Welcome to the solution video for homework 37, where we're going to be going over problem 6 from section 9.3 and problem 4 from section 9.4. Calculate the maximum deflection of a beam when we have the length, some distributed load, and we know that has a maximum bending stress. We also know that the cross-section is square and we have its elasticity. Use the formula of example 9-1. So the formula for 9-1 is the following. If we look at this, it's a function of Q, L, E, and I. We have three of these four things. We don't have our inertia, but because it is a square, we can find that, not too hard. However, we still don't have any information for our B. But that does give us a sigma. So I'm going to say, based on my bending stress, I can see if I can use my sigma to find my delta. So I can find my M by looking at my beam, and this is what it's going to be. The maximum moment here. This isn't a moment as a function of x, but my maximum moment would be QL squared over 8. C is B halves, and I is B fourths over 12. So if your initial thought is, okay, well I can just solve for I and plug that in, super close. However, you can't do that because there's also a B in my C value, and so I'm going to be solving for B. So if I put my M, C, and I over here and solve for B, this is what I'm going to get, and that is what I can plug into my I, which I'm plugging into my delta. Now I have a delta that's a function of only known values, so I can plug and chug and get that the maximum deflection is 15 millimeters. A beam has uniform load, a sliding support at one end, and a spring support of stiffness K at the other end. Derive the equation of the deflection curve, starting with the third order differential equation, and determine the angle of rotation at support B. So the third order differential equation, which it's asking us to start with, is this equation. And if we want to find the deflection curve, we're going to have to integrate a bunch of times because V, without any derivatives, is our negative deflection curve. So looking at this, knowing I need to integrate, and we're going to be integrating with respect to X, V here, the capital V, our shear, is our only thing that is a function of X, but I still need to figure out what it is. So I'm going to make a shear diagram. And looking at my graph here, there can't be a reaction on the left because we have sliding supports. So that's going to start at 0. It's going to go down by my slope QL, and my reaction B is going to bring it back up. So my shear as a function of X is just going to be simply negative QX. Now this I can integrate, and this is what I'll have. Now the integral of my shear is my moment. So EIV double prime equals this, and remember we have a plus C here. This is where boundary conditions become important. So I have to say, alright, I have a C here and I need to find out what the value of my C is. And it has to equal a moment. So I can say, well, if I look at my beam, what location do I know the value of my moment? We have a moment at reaction A, but we don't know what it is. But what we do know is that my reaction B, we cannot have a moment because we only have a spring there. It's not possible to have a moment at that location. So I can say at my L location, my moment has to equal 0. So my negative QL halves plus C portion has to equal 0. Then solve for C so that my equation works, and that is what I'm going to plug in before I do my next integration iteration. Now the integral of my M is negative EI theta. So I now have to find boundary conditions for my theta. And remember, theta means our slope. It's the negative of our slope. So I can look over here at my diagram again. Where am I going to know the slope? At my L distance, I won't know it because we can have a slope and that's fine, there's a spring. However, at x equals 0, I have to have a slope of 0 because I have a moment arm that's making sure that it stays perfectly horizontal. So theta of 0 equals 0, and I find out, oh, C2 is 0, and so easy peasy, we can do our next portion of integration. And then I also divided by EI here, just so we have less math to do. And last part here, I need to find some boundary condition for my displacement. There's no way for me to know my displacement at A, but B, I can find out. I know that the only reactive force, so the force that's holding my entire system statically in the vertical direction, is at point B. And so that's going to be my QL divided by whatever my K stiffness is. And thus, we can plug in our K here. Now that I have this equation, I need to keep going because I have been asked to solve for my delta. And this is my negative delta, and I also still have to find out what C allows me to have this delta at my L position. That C is this, so I can plug that in, negate it, and this is my solution for part A. Next, we need to find the slope at part B, which conveniently we have all the information we need to do already. So I have my V prime I solved for earlier. All I need to do is divide by EI because I had my EI multiplied by my equation, and this is my answer. Alright, boundary conditions is pretty much the only thing different between what we're doing today and what we did last time, because last time we said, okay, well, if my V is negative delta, I can take the derivative and find my negative slope. If I take my derivative again and multiply it by EI, then I get my moment, and then so forth for the rest of my important values here. But if we are given some of the other information, we have to go backwards, then we have to integrate as many times until we find the information we need. And every time we integrate, there's going to be a plus C. Now there is no perfect one way to say this is how you find boundary conditions. It really is just a mental exercise. You have to look at your beam and kind of think to yourself, what information do I know, or what information can I know? You can think to yourself, where is the slope 0? Or where is my moment 0, or where do I know what my moment is, and so forth for each one. It is most likely that you'll know the information for one of these at the ends of your beam, or perhaps in the exact middle. It is possible that you have some other locations where you can analyze. However, go to those first, and hopefully you can discover that you have some of that information. Now, if you are trying to figure out, say, when is my value positive or negative, so maybe you're saying, okay, I know what the magnitude, say, is of my theta at some location, but is it positive or is it negative? And this here, these arrows will tell you if something is positive or negative. So for your V, if your displacement, your V, is above your flat line, then it's positive delta. If it's below, it's positive. And for your theta, when it is going clockwise, it is positive. And since theta is a slope, maybe saying clockwise isn't too intuitive for everyone. If you cut a differential and you're looking at a small slice, if the left side is higher than your right side, then it is positive. Or in other words, if it is going downward, from the left to right, if it goes downward, then your theta is positive. Alright, I hope that was helpful, and good luck on your homework.